This video is going to practice drawing Lewis dot structures. So you can draw Lewis dot structures using single atoms, although it is rare. We're going to start our discussion with that. So we're going to look at boron. We're going to draw the Lewis dot structure of boron. Boron has 3 valence electrons. It's element number 5. You can see that here. It has 2 inner core electrons in the 1s subshell, and then it has a 2s1 and a 2p1. So it has 3 valence electrons, and you draw those with 3 dots. Those 3 dots can either be on 3 different sides of the element symbol, or you can put 2 together and then put 1 by itself, either one. Now, I know it has 3 valence electrons. You can either use the electron configuration to figure that out, 1s2, 2s2, 2p1. And so the valence electrons would be those in the outermost shell. Or you could use the atomic orbital diagram. Or what's easiest is to just simply use the periodic table. Since boron is in group 3a, I know it has 3 valence electrons. So group 1 has 1, group 2 has 2. We typically ignore the transition metals when we do Lewis dot structures. Group 3 has 3, 4 has 4, etc. until we get to group 8, which are the noble gases, and those have a full valence shell or 8 electrons. Now, this is related to the octet rule. The octet rule states that atoms will gain, lose, or share electrons until they have a full valence shell. For most elements, that means 8 valence electrons. Obviously, for hydrogen and helium, that means that it only will fill with 2. Now, if we continue this idea of the octet rule, metals, like these guys, they tend to lose electrons in order to get a full octet, and they form cations. Over here, these nonmetals near the right, they tend to gain electrons until they have a full shell, and they form anions, those shown in green here. A lot of these guys in the middle, I think I skipped over that. Let me get that back over here. These guys here in the middle, these nonmetals here, they tend to share electrons to get a full shell. And so these ones in green may gain electrons to form anions, or they may share electrons to get an octet. But either way, everybody wants 8. Everybody wants a full valence shell. Now, let's look at some other atoms. Sodium's Lewis dot structure, it has a single valence electron. Magnesium has 2. You can draw them together or on opposite sides. Let's do carbon, oxygen, and nitrogen. And chlorine. Now, those are all up here. Carbon, nitrogen, oxygen, chlorine is down here. So carbon has 4 valence electrons, nitrogen has 5, oxygen has 6, and chlorine has 7. So if we draw those dots in there, we get 1, 2, 3, 4. Again, you can draw them all on opposite sides, or you can draw them in pairs. 1, 2, 3, 4. So here you can see I've drawn these in paired, 3 pairs versus separated. You can draw them either 2 together as pairs or single electrons. But you can see that only 4 pairs fit around a given atom, right? That's the octet. That's the idea of 8. Okay, so I could have put two paired together, and then these 2 down here could have been separated on the other 2 sides. So that's what I'm drawing here. 1, 2, 2 pairs, and then I'm going to draw the others separated. Either of those is fine. Nitrogen has 5. 1, 2, 3, 4, 5. Chlorine has 7. There's only one real way to do that. You've got 3 pairs and 1 by itself. Now, normally we use Lewis dot structures to draw molecules, and so here we have a single carbon atom combining with 4 separate hydrogen atoms. The carbon is going to share each of its 4 valence electrons with hydrogen. Hydrogen brings 1 valence electron, which it's going to share. And so you can see the hydrogen's electrons are shown in red, and the carbon is shown in black with its valence electrons also in black. Now, we often show these pairs of electrons as lines. And so usually in a Lewis dot structure, a covalent bond, a single covalent bond is shown with a line, and that is understood to be the sharing of 2 valence electrons. So those are the same. 1 line equals 1 covalent bond, which is 2 shared electrons. Now let's do this molecule. So BCl3 boron trichloride, the first step when you're drawing a Lewis dot structure is to count the total number of valence electrons. So here boron has 3, and each chlorine has 7. And so step 1, we add up the valence electrons. Boron contributes 3, each chlorine contributes 7. That's based on the periodic table, right? Boron is in group 3, chlorine is in group 7. So you add all those up and you get 24 valence electrons. That's number 1. Number 2, you're going to connect the atoms with single bonds. So boron is the central atom here. This connecting the atoms is something that sounds really simple, but you need to practice this because it's not always obvious. Now, one little tidbit of information here, that's a little trick, is that usually when a formula is written with this format, where you have a single atom, boron, that I've represented here with an A, followed by a whole set of the same atoms with a number here, okay? So this is what we would call a binary molecule, where it has only two elements present. And the first one, there's only one of, and then the second kind of element, there's several of. These usually have the structural formula where the central atom is the first one that is listed, and the other atoms sort of radiate out from that central atom. And so that's typically true. So when we draw this, I'm going to draw boron in the center with chlorines attached. Now, we're going to revisit tips on drawing these later because there's some other little added tips. Once you've practiced them enough, you will see that, for example, carbon always tends to form 4 total bonds. Now, it might be some combination of single bonds, double bonds, and triple bonds, but so a triple bond would count as 3 bonds, right? So carbon they always add up to 4. Oxygen typically forms 2 bonds, and therefore it has 2 lone pairs attached to it. Nitrogen typically forms 3 bonds, although sometimes it can form 4. Hydrogen always forms 1. The halogens, like chlorine and fluorine, and you can see chlorine in this molecule here, the halogens almost always only form 1 bond, and that leaves them with 3 lone pairs. So there are some general rules that you will see, sort of some trends that will help you draw these molecules. Now, step 3 on our list of steps to finish our structure are 1, count the valence electrons and add them all up. 2, we're going to connect the atoms with single bonds like we did here. Number 3, we're going to start adding electrons until we get to the total, which is 24. So number 3, add electrons giving all atoms an octet until the total is reached. So we're going to start adding electrons to chlorine. So first, the 3 bonds we drew, that adds up to 6. 2, 4, 6. 2 for each single bond. Now I'm going to add lone pairs to chlorine. So I've got 6, and then this chlorine has 3 lone pairs. So 2, 4, 6, 8, 10, 12 I've drawn so far. 14, 16, 18, 20, 22, 24. Now, I'm actually finished on this structure. And this, I shouldn't have picked this molecule to start with, but I did, unfortunately. Boron is actually an exception to the octet rule. Boron is somewhat happy with just 6 electrons, and so it is okay with fewer than an octet. I should definitely not have started with this one, but we'll revisit the exceptions to the octet rule at the end. If you were not using boron here, then you would say that boron did not have an octet, and you would try to give it an octet. We're going to do some practice problems where you'll use double and triple bonds in a few minutes. But because we started with this unusual exception, stupidly, then we're actually finished here. Boron has 6 electrons, which boron is happy with. Each of the chlorines has 8, and so each chlorine has 6 that come from the 3 lone pairs, and then 2 more that come from the bonded pair. So 2, 4, 6, 8 for each chlorine. So right here I wrote boron is unusual and that it is satisfied with just 6. So that was dumb of me to pick that one. So let's move on and do some more examples. Here we have ammonia. Nitrogen has 5 valence electrons. Each hydrogen has 1. That gives us 8 total valence electrons. So now when we add these up, that's for step 1, 8 valence electrons. Step 2, connect the atoms with single bonds. So here I have nitrogen with 3 singly bonded hydrogens. Next, I'm going to add electrons up to 8, giving everybody an octet. Now, so far I've drawn 6, right, with the 3 covalent bonds. And each hydrogen is satisfied because it can't have more than 2 because it's in its valence electrons are in the first shell, which only houses 2 total electrons. So the hydrogens are now satisfied. The nitrogen is where I'm going to place that last pair of electrons. So I'm going to put a lone pair on nitrogen, sorry. And now when we look, each hydrogen has 2, which is good, and the nitrogen in the center has 2, 4, 6, 8, 3 bonded pairs and 1 lone pair. So that one is done. Finished. And number 4, we're going to ask ourselves the question, do all atoms have an octet? In this case, the answer is yes. If the answer were no, you would use double bonds and triple bonds to satisfy the octet. In this case, they do. Now we're going to move on. We're going to do carbon dioxide. So we count the number of valence electrons, 4 for carbon and 6 for hydrogen or oxygen. That adds up to 16 total. We connect with single bonds with carbon in the middle. We add electrons until we get to 16. So far with the 2 bonds we have 4, and now I'm adding lone pairs, 6, 8, 10, 12, 14, 16. Now I'm done. I can't add any more because I only have 16 to put in. So number 4 is, do all atoms have an octet? And that's a question you have to ask. And then you look at oxygen. Oxygen appears to be satisfied because the oxygen on the left, because it has 2, 4, 6 from the lone pairs, and then another 2 adds up to 8 from the bonded pair. So the oxygen on the right also has 8, 2, 4, 6 for the lone pairs, and then 8 from the 2 additional shared pair. So each oxygen has an octet, but the carbon in the center only has 4 electrons. So the oxygens are good, but the carbon is not. So if you have fewer than an octet for anybody other than like hydrogen or boron or helium, then you need to force oxygen to share more. Oxygen is being pretty stingy here. He has electrons that he could share with carbon because carbon is missing some electrons. So we're going to move a lone pair down to be a shared pair. We're going to cross these out and put it here. Now we're going to check again, see if we have an octet. The oxygen on the left is happy, the oxygen on the right is happy, but carbon in the center still only has 2, 4, 6 electrons. So that's still not enough. We're going to force this oxygen on the right to share. We're going to cross them out and move them to a shared pair. And we're going to ask one more time, does it have an octet? And oxygen on the left, yes, yes, yes. And so all 3 of them do. And so our final structure is going to look like this. Now it doesn't matter if you put the lone pairs on oxygen. These lone pairs I drew up and down. It doesn't really matter if you put them there or if you put them somewhere else. I just happen to put them there. But they do need to be on oxygen, right? So in that last structure, you have to have a carbon with 2 doubly bonded oxygens, right? The carbon in the center, 2 double bonds, each to an oxygen. And each oxygen should have 2 lone pairs. Now you can put them above and below, or you can put 1 lone pair on the end here and another one on the top. It doesn't really matter. But we generally pair them, okay? This is actually the most common way we show CO2. Now, cyanide ion, we're going to add up electrons. So we have 4 valence electrons for carbon because it's in group 4, 5 for nitrogen because it's in group 5. Now we're going to add 1 because this molecule has an overall -1 charge. This is a polyatomic ion. And so that's going to add a step. In step 1 where you add up valence electrons, when you add valence electrons up, you add extra electrons for any negative charges. So this is -1, so we add 1 electron. But if it were a -2, you would add 2 electrons. If it were a -3, you would add 3 electrons. However many negative charges you have overall, you add an extra electron for each one. If it is a cation, then you're going to subtract electrons for cations. You're going to subtract an electron for each positive charge. So if you have a +2 overall charge, you're going to subtract 2 electrons from the total. So now we get 10 electrons total for cyanide. We're going to connect it with a single bond, and we're going to add valence electrons until we get to 10. So here I've drawn 2, 4, 6, 8, 10 valence electrons on cyanide. And then next I'm going to ask if everybody has an octet. And we're going to look at carbon and nitrogen. Carbon does not, and neither does nitrogen. Carbon only has 6, 2, 4, 6, and nitrogen only has 6, 2, 4, 6. So if not every atom is satisfied with an octet, that wants an octet, then we're going to have to force them to share more. So we're going to move a lone pair down to be a shared pair. And next we're going to ask again, does everybody have an octet? And so carbon in this case does not, because he only has four shared electrons and 2 lone pair electrons. The nitrogen, however, is satisfied, right? Nitrogen, I put an X, but nitrogen does have 8, 2, 4, 6, 8. Now we're gonna, but because carbon is not happy, he doesn't have an octet, we're going to force nitrogen to share one of his lone pairs as well. Now we're going to ask if everybody has an octet, and carbon does 2, 4, 6, 8, and nitrogen does 2, 4, 6, 8. I'm just counting them all up, 2, 4, 6, 8. So now they both have an octet, so this is the final structure of cyanide, except, oh, I need to add in brackets. So since this has an overall charge, we have to add brackets and a -1 charge to the outside. So that's going to be what you forget. Your Lewis dot structure for a polyatomic ion always has to have brackets, and the overall charge is on the outside of the brackets. So don't forget that. That'll cost you some number of points if you don't have it. So let's move on. Resonance structures, when taken together, contribute to what's called a resonance hybrid. And so you're going to see resonance structures whenever you have a Lewis dot structure. Let's say this one on the left. This is nitrate ion. And the image, the model of nitrate is shown here with the blue nitrogen in the center and the 3 oxygens on the outside. So let's say this is the final Lewis dot structure that you would have gotten for nitrate on the left. But you can see that the doubly bonded oxygen is at the top. You could have just as easily put the double bond down here into the left or down into the right. And so whenever you have a Lewis dot structure that could have had double bonds in other places and been the same, right, the same identical, and you had a hard time picking which one, that means that structure exists as resonance structures. So because these are 3 equal Lewis dot structures that solve the problem, that answer the question of how to draw this Lewis dot structure, then these 3 would be represented. You need all 3 of them to truly represent the structure. So resonance structures, the way we think about those is the true structure is a hybrid of these 3. And so if I draw what that would look like, then you would have a nitrogen in the center, and you would have sort of 1 1/3 bond to each of these, 1 1/3 bonds for all 3 of these. They're all equal to each other. And so by 1 1/3 bonds, what I mean is that, when you look at the bond strength, how much energy is required to break it, and when you look at the bond length, right, how long or short is the bond, we learned in a previous chapter that single bonds are weaker and longer than double bonds, which are weaker and longer than triple bonds. And so this would be partway between a single bond and a double bond in terms of its strength and in terms of its bond length. And so it truly is a 1 1/partial or 1 1/3 bonds. Also, that negative charge on the outside you see here is really shared among these 3 oxygens. And so you end up with a -1/3 charge on all 3 oxygen atoms, and that adds up to -1 overall. So we do have one resonance structure shown here. Unfortunately, it's the same example that was given in the problem before, but we will practice some problems and you will see what resonance structures look like. Now we're going to do this practice problem, draw the Lewis dot structure for the following compounds. So first we're going to start with carbon tetrabromide. Carbon has 4 valence electrons and each bromine has 7. That adds up to 32. Step 2, connect with single bonds. Step 3, we're going to add electrons until we get to 32. So far I've drawn 8. Now if I give each bromine 3 lone pairs and the carbon gets no lone pairs and I add these all up, I should get 32. And so this is actually finished structure. That's the end. And then we're going to check and make sure everybody has an octet. And the answer is yes. All the bromines and the carbon have an octet. Next, this is potassium hydride. And so we talked briefly about Lewis dot structures for ionic compounds earlier. And this is the one you're going to miss because it's an ionic compound. But remember, ions have Lewis dot structures where you show that the cation has lost some of its valence electrons and the anions have gained some valence electrons. So potassium is just K with a positive charge. And so neutral potassium is shown here. It has a single valence electron because it's in group 1. If we remove that valence electron, it has no valence electrons and it has an overall charge of +1. Because there are no dots here, you don't have to include brackets. You only need brackets when there are multiple atoms or valence lone pairs of electrons that need to still be shown. Hydrogen, when it forms hydride, this is neutral hydrogen here on the left with a single valence electron here. When we add an electron to that, we end up getting 2 electrons, and we usually pair them when they're an anion like this. And so this has brackets around it because it has electrons on it, it has the dots, and we put a -1 charge on the outside. So when we draw this structure overall, you draw them next to each other, just like this, and this would be the final answer. So ionic compounds are held together by mutual attraction, not by covalent bonds. And so you don't draw lines between them like you would for a covalent bond. You just draw them right next to each other. That implies that they're stuck together, but not through sharing of electrons, just through the positive-negative attraction. Number 3 is nitrate. Nitrate was the example we gave in the last one. If we drew this Lewis dot structure, we would get 5 valence electrons for nitrogen and 6 for each hydrogen. I'm sorry, 6 for each oxygen. Then we're going to add 1 to the overall because it has a -1 overall charge. That gives us 24 electrons. When we add this up, now we're going to connect each atom with single bonds. Now, when we add in electrons to get to 24, we have 2, 4, 6 from the covalent bonds, and then each oxygen has 3 lone pairs that I've drawn here. And so I'm done. I've added 24 valence electrons, but the problem is that the nitrogen in the center does not have an octet, and so, but each of the oxygens does. And so if we force one oxygen to share, that will give everybody an octet. So if we take, so here I'm trying to figure out if it has an octet. I'm saying yes, 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 no. And so we're going to force some sharing here. We're going to erase those and put them here. So this is the final structure, but as we mentioned before, except we need the brackets and the charge. As we mentioned before, if I could have just as easily put the double bond on the left or at the top, that means that there are actually 3 resonance structures. The different resonance structures just have different locations of the double bond. Okay, and that's the only thing that's different about them. You're not rotating the molecule, you're just drawing an alternative structure that meets all the requirements and is equal in energy to the first one. So these oxygen atoms, it's not that we're moving it, it's not we're rotating the molecule, we're just moving this double bond to be up here. And remember, the true structure would be a hybrid of these 3. And to answer the question, you have to have all 3 structures there. If it asks you to draw the Lewis dot structure, you need all 3 resonance structures to get full credit. Now finally, H2CO, this is formaldehyde. We're going to add up valence electrons and we get to 12. If we connect with single bonds, the carbon is in the center. And we're going to draw this with single bonds, and we're going to add in electrons until we get to the total of 12. And at this point, we have 12. And we're going to ask if we have an octet for all the atoms. The hydrogens each have 2, which is good. The oxygen has 8, but the carbon does not have an octet. He only has 6, 2, 4, 6. So we're going to force oxygen to share one of his lone pairs with carbon, and it's going to form a double bond. And so this is the final structure of formaldehyde, where the carbon is doubly bonded to the oxygen. The oxygen has 2 lone pairs, and the carbon also has 2 singly attached hydrogens. Now this is a good example of what we talked about earlier, where after you've practiced these enough, you'll see that hydrogen always only forms 1 single bond, and it never has any lone pairs. Carbon always forms 4 bonds, 1, 2, 3, 4. Now it might be, like for example, if you look back at the carbon tetrabromide structure, it might be 4 single bonds like it was there. Or in this case, it's a combination of 2 single bonds and 1 double bond. Or you could have 1 triple bond and 1 double bond. Or you could have 2 double bonds, just like in carbon dioxide. Whatever the case may be, the number of lines touching carbon should add up to 4. And it has no lone pairs because 4 bonds will give it an octet. Now, this is typically what oxygen does in almost every situation. Oxygen typically forms two bonds, whether or not it's a single bond, a single double bond like this, or two single bonds like in H2O. If you add up the lines, they will add up to two, and then that leaves oxygen with two lone pairs of electrons almost all the time. So let's move on. BH3 is boron trihydride. These two are exceptions to the octet rule. Boron is happy with just 6 electrons around it, and this is going to be the final structure for boron trihydride. There's no other way of drawing this structure because there are no other electrons to share. Hydrogen doesn't have any lone pairs. So PCl5, phosphorus is here, and chlorine, that has 5 valence electrons. And then chlorine has 7. So when we add these up, we get 40 electrons. So if we connect the phosphorus with 5 singly bonded chlorines and we add valence electrons to chlorine to get to 40, then we're done here. But what you might notice is that phosphorus has more than 8. It has more than an octet. Each of the chlorines has 8, but phosphorus has 10. And so it's possible for some elements to expand their octet. It has more than an octet. And so it's possible for this to happen, and that is okay for certain elements. So if you look here, any element beyond the third row and beyond, is going to have empty d orbitals, and it can house its extra electrons in those empty d orbitals. And so this says only rows 3 and higher can expand their octet. And so hydrogen through neon cannot. And sodium and magnesium are going to form ions anyway, so you don't have to worry about that. So will aluminum, actually. But silicon, phosphorus, sulfur, chlorine, all the way down to element 118, those can all expand their octets if necessary. You'll see it's more common for certain elements than others. For example, phosphorus very commonly expands its octet, so does sulfur. Some of these others, selenium, sometimes you see it. So we'll see a few examples of that.